Assalamualaikum warahmatullahi wabarakatuh. Now our discussion is about the equilibrium of a rigid body. And previously I have discussed about the equilibrium of a particle. The basic of this is similar, because if you want to say that the rigid body in equilibrium, it will be in equilibrium when the resultant of forces acting on it is zero. So if all of the forces, whether it's the resultant or sigma f, or it will be can refer to the fy or fx, both of them have to be zero, and also the moment it have to be zero. When this condition attained by a rigid body, so this rigid body, it will be in a state condition, or in other words we can say that it is in equilibrium conditions. That's the basic of equilibrium of a rigid body. And then in the equilibrium of a body in two-dimensional, we will discuss about the three-dimensional in the next video. And now in this video we only discuss about the two-dimensional equilibrium of a body, and then the system isolations and free body diagrams. Please remember that we will work with the mechanic system, where in a mechanical system we will find some body or group of bodies, and when we decide to analyze the mechanical system of a body, we then need to treat this body or combination as a single body isolated from all surrounding bodies. That's the first conditions. So we have to isolate the body, the single body, from all surrounding bodies. And the isolation is accomplished by means of the free body diagrams. With the free body diagrams is our hint here. It is the hint that will be very helpful for us, that the free body diagram is the most important single step in the solution of the mechanics. So please remember this one, that we have to create the free body diagrams, because it is the most important single step to solve all of the problems in mechanics. But before we attempting to draw a free body diagram, we have to remember and we have to recall the basic characteristic of a force. All of the basic characteristics of a force can be either internal or external to the system, or maybe application of both applied and reactive forces, or maybe concentrated or distributed. All of the basic characteristics of a force, we have to remember and recall this. And now we will start with the modeling of the action forces. This first modeling, I will write this one is the first modeling. It is the flexible cable, belt, chain, or rope, or maybe it's I will write the cable. And we have the two conditions here for the cable. The first condition, weight of cable negligible, and the second condition is the weight of cable not negligible. When the tension of T, here is the T, is large, it's very large compared with the weight of cable, so we can neglect the cable, the weight of cable. And then we have to form the cable in a straight line. So the cable, for example, like this one, so it will be assumed that the cable forms a straight line. But when the cable weight is not negligible, for the second condition, this one, so the sec of the cable become important. So you have to know that the sec of this cable. So you have to use the sec of the cable. We have to know the numbers of theta, the magnitude of theta, and you know the sec of this cable. So maybe you can say like this one. Is for the first condition and is for the second condition. And then for the second model, it's the smooth surface. For the smooth surface, we can assume that it is very smooth surface, though we know that no actual surface are perfectly smooth, but we can assume that it is the smooth surfaces. And then when it is the smooth surfaces, we only have the normal line. For this one, for the first modeling, it have to be the tension. Is the characteristic of the cable, it will be the tension, and this one should be the compressions. And also for the rough surface, it's a little bit different with the smooth surface. Is for the rough surface, in this rough surface, it can be resolved into a tangential or frictional components of the F and normal components. It is the normal component. And remember, when we have two forces concurrent in a bottom point, so we will have the resultant of that. In this case, you will write this one. Here is the resultant. So the rough surface, they will have 3 forces here. Actually 2 forces, but it can be replaced with 1. It is called as a resultant. And then for the pin connection, it is number 4 for the pin connection. In the pin connection, actually it is separated into 2 different pins, where the first one is a pin free to turn and the second one is pin not free to turn. For the pin free to turn, so they can turn to any different magnitude, so they only have the R, X and R, Y. Okay. And for the pin is for free to turn, and for the not free to turn, they will have the Rx, Ry, and also they tend to have the moment. And then for the fifth modeling, it is the roller support. You can change anything, but it's referred to the roller support. Both it is the roller, rocker, or ball support, like this one. It's they're different, but actually it have the similar force here. So you have only the normal force for this one, and also for the other one it will be like this. It also have the normal force. That is for the roller support. And then for the freely sliding guide, it's the sixth modeling of the freely sliding guide. For the freely sliding guide, they also have only the normal force, and it is the compression. Obviously, remember, you can check which one is the compression or the tension. And actually, for the all of sense here, you can give the assumption in the first. You can assume that all of that is in a positive, but when the result you obtain in the negative, so it's meant that they actually have to be in the opposite sense from your first assumption. So you can give the initial assumption for all of your forces, depend on the member of the force. And then the seventh is a built-in or fixed support. We call it as a fixed support. But a fixed support, they are in a fixed position, so it will have the forces here, and also the vertical forces here, and also because they have to in a fixed condition, so they will, maybe they have any beam or other force here, they tend to get the moment, and it will consist of three forces, where the F refers to the forces and axial forces, and V refers to a transverse force, V or shear forces, to refer to the shear forces, and the M is the bending moment to prevent any rotation. So the function of moment here to prevent any rotation, and it will be the same. It's only different. It'll fix by plug the beam to the wall, and here using the weld. They weld the beam to the wall, so it's also the fixed support, and it's really the same. And for this one, for the eighth one, I have this. I have explained about this one in the previous video. You can check in the previous video about the spring, and then in the ninth here, it's referred to the gravitational attraction. It's the gravitational attraction. So the weight of this, it will be referred to the mass times gravitational constant. Okay, let's have a try to see these examples of free body diagrams. In a plane truss, for the first condition of the plane truss, weight of truss assumed negligible compared with the P. So it means that the tension of the P is very large. So, and then the weight of truss, it can be negligible. If you have this condition, so please remember that it is pin connection, and this one is a roller support. Pin connection, they have two forces here in A, Y and A, X, but this only have a normal forces, and the P is the forces that exert on this plane truss. And the second one is a cantilever. The first one is the second one, and a cantilever beam. On the cantilever beam, please see that it is the fixed connection. When it is the fixed connection, and we have three forces here, the first force is second and the third one, so they have to then make it in a condition, a steady condition. It is the opposite of this one, and also have the shears have to be to the vertical, because we have three forces and one weighted, all of them to the bottom of this one, so you have to be up, and all of that tend to rotate counterclockwise. So the moment here, they have to prevent how it cannot rotate, so it will be counterclockwise. That's what I mean, that this one is the clockwise, and the moment it have to be counterclockwise to prevent the rotation. And then for the beam, smooth surfaces contact at A with the mass M. It is the normal line. It is the normal line, so we have, and here the normal force and we have the moment here. And please check this one. It is the pin connection. For the pin connection, they have two forces component here, the Bx and By, x direction in y directions, and the P is the forces exerted on the beam. Sorry, I mean that exert on the beam, and the weight of the beam, it is in the center of this beam. And the fourth is the rigid system of interconnected bodies analyzed as a single unit. Is this the external force exerted on this system of the body? And we have this one is a roller support, and it is the pin connection. Roller support always have one component only, and this one for the pin connections they have two components, and it is the weight, where the weight of that is referred to the mass times gravitational constant. And that's all for the example how to create the free body diagram. So now you have to learn how to create your own free body diagrams. Now we are moving to the examples. The mass center G of the 104,400 kilograms rear engine car is located as shown in the figure. Determine the normal force under each tire when the car is in equilibrium. State any assumptions if you have the assumptions. To solve this one, please, we have to write first that do we have any assumption? Of course we have any assumptions. Our assumption that is that the G, it is located in the midway between left and right. So they are in the mid of this one, in the left and right door of this car. So they're located in the midway of that, in the between of the left and right. Why we have to assume this? Because the different assumption, it will create any different center of the G. And when the location of G is not in the center, you have to make other calculation. So to make it easier, I gonna assume that the G midway between left and right. And after this, after we have the assumption, directly we have to find the sigma forces, all of the forces that were exerted on this car. Because the body of this one is the car, so we have to write this as a sigma F, which will be 0. And we found any fx? We didn't find any fx, so all of this here is the fy. Please remember that we have two tires. The engine is the middle of the tires, and we have two front tires and two tires, two rear tires. So okay, I can write this one. So we have, here is the F and here is the R, and the center of the G maybe it's located about here, and then it says 934 millimeters, and here is 100,386 millimeters. And please remember that the rear engine is located between two tires, the front tires. So I will write this one as a 2F or 2R here. It's also for the two rear tires. And we have to determine the normal force under each tires. Because we have the two tires, we have to find each tire. So two normal force of the front tires, and here two normal force of the rear tires. So this one, what is working on this body is a two normal force plus two normal force. They're working in the top. And please remember that it is the center G is located here in the center of this one, and the weight, the mass of this one is 100 and 1400. So the weight here will be m times g, and you'll have it's a negative 1400 times 9,81 is 0. So we cannot find any normal force at the front. Sorry, this one is the rear, or the normal force of the rear. We continue to obtain the sigma f. I'm sorry, I mean the moment first. We can find any moment. We can find the moment of mr. You can find also the moment of mf here to get one of them. But I choose here, I want to find the mf sigma mr moment about point f. So you have negative 1400 times 9,81, and it is the distance between f to the g is 1386 divided to this one, and also plus 2nr. 2nr here is 2nr times the distance of this one, 964 plus 1386. So we have the nr here is the 4060, and then we can substitute this result to this equation. And after we substitute this one, we obtain the normal force of tire front is 2817. Okay, we have answered the equation that we have to determine the normal force under each tire. So in each tire, each tire of the rear is about the 4050, and each tire of the front tire is a 2870. Let's come to the second examples of these problems. A carpenter carries a 12-pound 2-inch by 4-inch board shown. What downward force does he feel on his shoulder? So the question is about the downward force that the carpenter feels on his shoulders, on this one. Firstly, you have to create the free body diagram, because it's very simple. Okay, now from this free body diagram, you can see that the B is here. Okay, here is the B. It's working to down the distance 1 inch. And here is the A with a 2-inch. And the beam weight mass is 12 pound. So 12 point actually is located in the center of the beam. In the center of the beam, we have the center located. The center of this beam is located here. So it's a 2-inch. So it's 2-inch, and another inch. 1 inch. So what downward of the force does the carpenter feels on his shoulders? So you can write that this one is directly to write this as sigma m on B. We cannot put this one in MA because it's what we're looking for. And then the assumption here is positive is the counterclockwise. It will be 0. And then we have the force is 12. The force is 12. and the force is a counter clockwise, so it will be the positive times the distance to B is a 3, negative, and A, because the A to this one, it is clockwise, and the distance of this one is a 2, it will be 0, so the normal force on A, it will be 18 pounds. So the force is that the downward on the carpenter's shoulder is 18 pounds. I think that's all for this discussion. Thank you so much. Assalamualaikum warahmatullahi wabarakatuh.